Okay, we might make a start if that's okay. We've got lecture 3 to do this afternoon, on respiration. And there's a couple of slides spilt over from lecture 2 that we need to get out of the way. And somebody said the recording cut out early on lecture 2, so I'm happy to repeat that today. Also, on the assumption that we couldn't dim the lights, which we can magically today, I changed the background of my slides to be white. They always say light black background for light room, dark background for dark room. Thinking this was going to be fairly bright, I had a white background, so I apologise if that's slightly awry. But nevertheless, that's maybe just more interest to me than you. What we're going to do for the bulk of today is to look at partial pressures and the partial pressures of the relevant gases in various parts of the body. So that will take the bulk of today's lecture. Before we do that, we left last week's lecture by looking at the mechanics of breathing. So basically we start with the mechanics of breathing, that is how and why we breathe. We're going to look then today at the partial pressures of the relevant gases. And then next week, because tomorrow's a clicker session, as you know, to review the first 3 lectures and online material. And then next week we'll talk about transportation of gases around the body. And then finally how we regulate that whole process, how the body regulates it. And in the last lecture we'll talk about some of the clinical applications to the information we've covered, which may be of interest. So I left the last lecture looking at this, which is basically contextualising some of the processes that we undertake when we breathe. Now, clearly and easily, and again, somebody's reminded me I shouldn't use a laser pointer. The mouse is better if you are online, so I'll do so. Very quickly, because I've discussed this already, and you'll notice, or hopefully notice, that all the values that I'm talking about are on the next overhead. So I've given you some summary values and some explanations so that you don't have to worry about writing everything down. Just observing this graph would be useful. You can see that you and I breathe approximately 500 mils of air per breath, which we call our tidal volume. So that's 500 mils volume of inhalation and 500 mils of expiration. And that's called the tidal volume. We don't work from an empty lung. We don't work, obviously, from a full lung. We work somewhere in between. Having said in between, probably a little less than half filled. And the reason for that becomes obvious in a moment. Because over and above our normal inspiratory breath or expiratory breath, we need to have a reserve. The reason you need to have a reserve is pretty self-evident. There are occasions that you need to increase the amount of oxygen that you're making available for the body. And more importantly, you also need to expire or exhale more carbon dioxide. So you remove more carbon dioxide from the body than you would normally. So we need to have those reserve volumes. And you can see our capacity, and I should say here, these numbers are based on the typical physiological individual who happens to be in a patriarchal science society, but I'll leave the sociologists to worry about that, happens to be a 70-kilogram male of about 20 years of age. Now, obviously, if you don't fit that demographic, your volumes may be slightly different, but you have to have a standard, and that's the standard. So you may be able to exhale more than your 500 mils, and for most of us, we can exhale about another litre, and that's called your expiratory reserve volume. Makes sense? It's in reserve. We've also got an inspiratory reserve volume, which is much bigger than our expiratory reserve volume. It's about over 3 litres of air that you can take in if you take your maximum breath to full lung capacity. Before we leave that, I ended last lecture by saying that try as you will, you can never empty your lung to zero volume. How and why is that important? Well, why it's important is fairly simple. If you had the capacity to breathe out as hard as you could to totally empty your lung, the alveoli would collapse, the surface tension would be so great, it would be nigh on impossible to voluntarily fill your lungs again. So that's why we don't want to do so. How's a little more complex. It's not a conscious thing, it's an automatic thing, but last week we spoke about pressures, and you might be aware that, you might recall that to exhale or expire air, you need to have a positive pressure in the lung tissue, which creates an imbalance of pressures and therefore air is pushed out of the lungs. And the more air you want to exhale, the greater that positive pressure has to be in your lung tissue. Now, if you're doing a maximum expiration, that positive pressure is so great, and I'm only talking about a few millimetres of mercury, but it's still so great that it's going to collapse those very small, delicate bronchioles. Not the big trachea or bronchi, they've got cartilaginous rings. Not the large bronchioles, because their walls are so thick, comparatively. But the very small ones will collapse with that external pressure. And obviously, if you collapse the bronchioles, to which the alveoli are attached, the alveoli can no longer empty totally their contents. So that's the how part of the question. And that remaining air in your lungs is called the residual volume, residue left over, and it's about 1 litre to 1.2 litres. And that means if you add all those volumes together, we have a total lung capacity, and we use the word capacity rather than volumes. Capacity means there's more than one volume added together. And so our total lung capacity of a typical individual is about 6 litres. That's the residual volume, your expiratory and inspiratory reserve volumes, and your tidal volume sum up to about 6 litres of air. Now that obviously changes depending, as I said, your size, and training can increase that as well. You might find elite athletes, particularly swimmers who use breathing specifically in their sport, would have perhaps greater total lung capacities. The other capacities I'm not particularly interested in, other than the vital capacity, which is relevant in that the name vital tells you it must be relevant, and it's basically the amount of air that you can move into or out of the lungs maximally. So your vital capacity is, as the diagram suggests, the maximum amount of air that you can breathe in from residual volume or breathe out from total lung capacity. So if your lung's totally full, breathe out as hard as you can. What volume can you breathe out? That's your vital capacity. And the flip side is empty your lungs as much as possible, breathe in as big as you can, same volume, vital capacity. Now the reason I'm focusing on that is that becomes clinically relevant. And we'll talk about that in later lectures, but certainly if you have a disease where your lungs are not as elastic as they should be, you'll have a small vital capacity because you can't stretch your lungs as much. And similarly, if your airways are too narrow because you've got asthma or some inflammatory disease, you may be able to get rid of all your vital capacity, but it's going to be much slower to do so. So clinicians or people doing the physiology prac will measure their vital capacity and measure how much of that they can move in 1 second. And that tells a bit about our health of our respiratory system. But we'll talk about that at another stage. This has no new information. It's basically the explanation and some values that I promised I would put up. And I don't know why one's in red and the others are in blue. And finally, before we start looking at partial pressures, we need to look at 2 really important distinctive definitions. And they're listed there, and in the next overhead, I give you values. but I just wanted to concentrate on the definition first. The first is something called pulmonary ventilation. Now, pulmonary means lungs or the entire respiratory system. Ventilation, another word for breathing. So basically, pulmonary ventilation is the amount of air that you move into and out of your respiratory system every minute. And it's pretty straightforward to calculate. It's basically tidal volume, how much you breathe per breath, times how many times you breathe per minute. And that's all good and well, and I'll put values to that in a second, but it clinically hasn't a lot of relevance. What's much more important clinically is something called alveolar ventilation, because that says how much fresh air do you get in and out of your alveoli per minute. Why do I make that distinction? Because the alveoli are the sites of gas exchange, and that's kind of why we breathe, to get air from the atmosphere into our alveoli so it can participate in gas exchange. And that's more relevant, and therefore calculating that is tidal volume minus your dead space. Now remember, the dead space was the volume of air that never reached the alveoli. It's in your trachea and bronchi and bronchioles. Can't participate in gas exchange. So for the purpose of respiration or gas exchange, it is wasted or useless air. So let's put some values and then we'll see why I make this distinction now. Our pulmonary ventilation is typically about 7 litres per minute, because each breath, as we said in the last overhead, is about 500 mils, and you and I breathe approximately 14 breaths per minute. 14 times half a litre is simply 7 litres. Now, how much of that 7 litres that you and I breathe per minute can actually participate in gas exchange? Far less than that. Because of each breath of 500 mils, 150 stays in the dead space, does not reach the alveoli. So in fact, we need to subtract that from our 500 mils, which gives us 350 mils. 350 times 14 is about a little less than 5 litres. So of the 7 litres that you breathe in and out of your respiratory system per minute, less than 5 can participate in gas exchange, and that's clinically relevant. There's the old story in the hospital, which I really don't have time to talk about, but I will anyway, because I kind of like my stories. Somebody who's very ill. Now, what often happens to somebody, or how do they exhibit in terms of breathing if in fact they are in pain or they are in some sort of distress? Your breathing becomes more rapid and much more shallow. Now, let's say somebody is only breathing about 200 mils per breath, which is not uncommon, and they're breathing 25 times, and I'm really stretching myself mathematically, 25 times per minute. So they're breathing fast and shallow. Their pulmonary ventilation is relatively normal. 25 times 200 is about 5 litres, so it's not a huge drop. But nevertheless, that person will probably suffer massive respiratory distress, because alveolar ventilation is much more important clinically. So how much can actually fresh air participate in gas exchange with those same figures? Well, if they're only breathing 200 mils and 150 is your dead space, that's not going to change, that's you. 50 mils times, what do we say, 25 breaths per minute, that's less than a litre. So you can see dropping their alveolar ventilation from nearly 5 litres to way less than a litre is going to have a big impact on that person, even though their pulmonary ventilation is almost normal. So that's why shallow, rapid breathing is a problem in terms of respiratory health and function, and it's the reason we need to be aware of these distinctive definitions. Now we've got that out of the way, we'll still talk about dead space, and we're going to talk about its relevance in partial pressures. And so the partial pressure part of this lecture is summarised by these 2 simplistic statements that I try and put at the beginning. Okay, today it's not the beginning, I was running late last time, forgive me, but towards the beginning of the lecture. So, oxygen and carbon dioxide. We're not really interested in nitrogen. For respiratory purposes, it's inert, it plays no particular function to our health, unless you're a deep sea diver and it tends to bubble out of solution and create emboli and kill you. But if you're not doing that, it's pretty well, we can ignore it. Oxygen and carbon dioxide diffuse between the alveoli and the pulmonary capillaries. So basically, air in the lungs, alveoli exchange with the capillaries surrounding the alveoli. And between the systemic capillaries going to your tissues and the working cells. So that's kind of where respiration occurs. So we've got pulmonary respiration and tissue respiration, doing kind of opposite things. And this is what, as I said earlier, is called gas exchange or respiration. Let's look at it in much more detail. Summary slide. Hopefully nothing too comprehensive or complex here. Respiration in tissues. Respiration, remember, gas exchange. I've said that 10 times. So in the tissues, it involves oxygen moving from your bloodstream to your cells, because that makes sense. In your tissues, your cells are using oxygen, you need to provide them with new stuff. And the cells, the working cells, are producing a waste gas called carbon dioxide. You need to get it out of the tissues, because too much carbon dioxide, for reasons we'll discuss next week, is toxic to the tissues and toxic to you. As I said, I'm sure in one of the online presentations, if you ask most people in the street, why do we breathe? They would say because we need oxygen. They wouldn't be wrong, but the physiologically preferable answer, why do we breathe? To get rid of carbon dioxide. You will die of carbon dioxide excess well before you die of lack of oxygen. So keep that in mind as we go through the following lectures. So in the lungs, it's the opposite. Respiration in the lungs involves oxygen diffusion from the alveoli, which comes from the atmosphere, to the capillaries, and carbon dioxide coming from the blood into the alveoli so we can get rid of it back into the atmosphere. Same thing, opposite direction. Now, what can influence respiration? Well, surface area influences respiration, and that's why the organ that has massive respiration, the lungs, is really well adapted, as I said online, to having a huge surface area. You might remember, alveoli, size of a tennis court, 70 square metres. At any one time you've got maybe 250 mils of blood. Paint 250 mils over a tennis court. That gives you the idea of how efficiently that gas exchange can occur. But it's also relevant for organs. If you've got an organ that's highly metabolic, needs lots of oxygen and getting rid of carbon dioxide, you will find it has a very big blood supply and an effective as possible surface area. So, partial pressure gradients can affect respiration. Obviously, as we said, gases move down concentration gradients. Without a concentration gradient, there will be no net movement. The bigger the concentration gradient, the bigger the net movement. So you and I try and achieve partial pressure or concentration gradients. We'll talk about that in a minute. And obviously rate of blood flow. Obviously you want to get the blood to the organ to maximise respiration. Now all three of those things we'll discuss in detail. This was just the prelude. Let's start looking at it. Professor Fick lauded appropriately in respiratory circles for coming up with the equation that basically summarises gas exchange or respiration in you and I. So this is an equation with which you need to be familiar. And that's why it has its own overhead and it has lots of explanations making sure you understand it, but I'll still go through it with you. How effectively you diffuse, in this example, gases, can be calculated by 4 basic factors. So any of these can change and it will change the rate of diffusion. So if you increase any of these top ones, you'll increase the rate of diffusion. If you increase the bottom one, you'll decrease the rate of diffusion because it's inversely proportional. So, how do we calculate diffusion? Firstly, a constant. It's called Crogg's constant. In fact, Crogg's diffusion constant. And the word solubility is relevant to that constant. The constant basically determines how soluble a gas is. Now you might say, why is that relevant to diffusion? Because where are you diffusing from and into? You're diffusing from the alveoli, which contains gas, into the blood, which is a liquid. Now, that won't happen if the gases aren't soluble. Or it'll happen differently if the gases are differently soluble. And they are. Carbon dioxide, much more soluble than oxygen. So the solubility of a gas certainly impacts on its capacity to diffuse from the alveoli to the blood. And that's why it's relevant. The surface area, as we discussed ad nauseum previously. The bigger the surface area, the more rapid the rate of diffusion will be. Fairly straightforward. The concentration gradient, that's what delta C means, the concentration gradient. In this case, it's a partial pressure gradient. I'll talk about that in a minute. But the concentration gradient, as I just said 2 or 3 minutes ago, bigger the concentration gradient, the more diffusion will occur. And after all, as you probably have thought about, and if not easy to think about, what are you doing when you take a bigger breath? You're basically getting more atmospheric gas, which is rich in oxygen and very deficient in carbon dioxide, into your alveoli, thus creating a bigger concentration gradient, thus increasing the rates of diffusion. And that's all you do when you take your big breath or blow more air out. And it's inversely proportional to thickness. So you want it as thin as possible. And that's why, as I said, the alveoli are, 0.02 microns thick. Don't quote me on that. I wrote it down somewhere, but I remember it as about 2/100ths of the diameter of a sheet of paper. That's how thin the surface is. Okay, so, but where might this be impacted? Well, if you have an infection, inflammation, anything which increases the thickness of your alveoli surface will reduce diffusion. And that's why people with emphysema, or people with asthma, or people with bronchial or alveolar disease will have compromised gas exchange. Okay? So a Fick equation answers all clinical criteria important to remember with regard to diffusion. What are we diffusing? Start with a very easy slider overhead. Major gases in the atmosphere: oxygen, carbon dioxide, by major I'd say relevant, nitrogen, and depending on the humidity of the environment, water vapour. So what are their proportional representation in the atmosphere? Well, on average, pretty closely similar all the time. 21% of our atmospheric gas is oxygen. Less than about 0.04% of the atmosphere is carbon dioxide. Very little. To all intents and purposes, there's virtually no carbon dioxide comparatively in the atmosphere. But it's why it gets a lot of publicity, because small changes impact greatly. Nitrogen makes up the difference. If it's not oxygen, not carbon dioxide, it's nitrogen, as I said. And depending on the humidity, water vapour makes the rest. In the tropics, it'll be higher. In the Arctic area, it'll be less, but an average figure, not a lot. Now, we're not particularly interested in nitrogen and water because we don't utilise those gases. We don't need those gases. So, in fact, We don't get our water from breathing, we get it from drinking. Nitrogen, as I said, is inert in terms of functionality. We don't use it, we don't really produce it too much, it's not really of consequence. But a lot of it's there, so we have to acknowledge it. Oxygen and carbon dioxide are the key players. Now, atmospheric gas has a pressure. And remember, Boyle's law was talking about things being in constant motion. So the molecules in the atmosphere are constantly moving, be it oxygen, carbon dioxide, nitrogen or water vapour. They're all moving. And they hit each other, they hit the walls, they hit the ceiling, they hit the floors, they hit us. And as they hit these objects, they impart a pressure, which can be measured conventionally by how long it can move a column of mercury. Mercury being a very viscous, heavy liquid metal. And so we happen to use mercury. It could have been anything. Some people are trying to move it to water, but mercury still works. So how far along a column can that pressure move mercury? So that explains the units. Anyway, whatever the units are, and they happen to be millimetres of mercury, the pressure is about 760 millimetres on average. That can and does change within a few percentage. So this is where partial pressure comes in. If the total pressure in the atmosphere is 760 millimetres of mercury and oxygen molecules make up 21% of them, because they all contribute equally, all they being all the molecules in the atmosphere, they all contribute to pressure equally, it stands to reason simplistically that oxygen's partial pressure, the part oxygen plays in that total pressure, is 21% of 760, which is about 160 millimetres of mercury. And that, my friends, is why the PO2 in the atmosphere is 160. Now be aware, you always have to say P, partial pressure of oxygen, in something. So PO2 of the atmosphere is 160 millimetres of mercury. Carbon dioxide, same equation, is about 0.3 millimetres of mercury. Not a lot. Nitrogen and water vapour we are going to ignore. So these figures, 160 and 0.3, are key figures to remember. That's in the atmosphere. Let's see what happens to those partial pressures as it is breathed into the body and moves around our circulatory system. And obviously they're going to change. Firstly, let's have a look at what it is in our lungs. Now, I'm sure nobody's naive enough to expect that the partial pressure of oxygen and carbon dioxide in the lungs, alveoli, will be the same as the atmosphere. It's going to be different for each of those three reasons. Firstly, and the least significant impact, is that we humidify air as we breathe it. Remember, you're moving air through a narrow, moist tube really, really rapidly. So obviously it's going to humidify the water, turn it into vapour, and that's going to proportionally reduce the partial pressures of oxygen and carbon dioxide. One reason. Much more importantly are points 2 and 3. We are mixing old and new air. Now, what does that mean? Now, I've got a diagram in the next slide to explain that, so I will dwell on that a little more, but for just getting the concept down now, breathe out what remains in your airways, your dead space. Gas that's come from the alveoli that has already participated in gas exchange. It's given up some of its oxygen. It's received lots of CO2. So when you breathe in, the first 150 mils that you breathe in is stale air. So it's not going to be atmospheric gas, it's the dead space. It's going to be low in oxygen and high in CO2. So obviously that's going to be a massive impact. And you might say, well, it's only a little bit. No, remember it's 150 mils of 500 mils. It's 30% of a normal breath is stale air. And finally, we're not breathing into a closed bucket. We're constantly removing oxygen. That's what diffusion's all about. And we're constantly adding CO2 to our alveoli. So because of that constant removal of oxygen and constant addition of CO2, the PO2 in our lungs is also, you would expect, to be less than the atmosphere, and the PCO2 would be higher. So 3 reasons, particularly reasons 2 and 3 are relevant. We have worked out, or I've actually told you, hopefully you're coming along for the ride, that the PO2 in the alveoli is going to be less than the atmosphere, PO2, and the PCO2 in the alveoli will be higher than the atmosphere. And obviously that's the case, otherwise I wouldn't be doing my job properly. Now, I said I was going to talk about the mixing of new and old air. Now, this diagram, which comes from Widmeyer, Silverthorne's not really as good for this diagram, but I've placed it on your LMS site, 1 per page or 3 per page if you'd prefer. So there's nothing too difficult about accessing it. Widmeyer uses colours to indicate the difference between fresh air and stale air. Now, I don't like using the word fresh air and stale air because it doesn't really mean much, but for this point I'm happy to go with those definitions. So, fresh air, that is air from the atmosphere, lots of oxygen, virtually no CO2, is in orange, and each time you breathe about 500 mils. Now, it said 450, you'll see why, it doesn't really matter, just for the maths. And alveolar gas is going to be stale air in purple. That is, it's already given up some of its oxygen and received additional CO2. So after breathing out, we are in this state on the left. The airways, that is your dead space, your conducting zone, contains stale air. Now you take a breath in, move to the right-hand panel of the diagram. The first 150 mils that goes into your alveoli is in fact stale air, followed by 300 mils of fresh air. The last 150 mils stays in the airways, obviously. So, in fact, only 2/3 of a typical breath that enters your alveoli is fresh air. There's lots of stories around this, but it also, in your chutes, it talks about assisted ventilation or mouth-to-mouth resuscitation and why breathing a little bit of air into a non-breathing person is good. Have a think about that orange bit in your airways and that'll answer your question in your workshops. But another time. Maybe I'll put a chute question on that in the clicker session. So, we've already established that PO2 is going to be less than the atmosphere, PCO2 is going to be more. Punchline, waiting a long time, over it, get to the punchline, here it is. PO2 in the alveolus, 100 millimetres of mercury, really easy number to remember. Like remembering numbers when they're easy. PCO2, 40, easy number to remember. So, exactly as we predicted, that's what it is. Now, this is normal breathing. Obviously, if you took a bigger than normal breath, you'd have more oxygen-rich atmospheric gas and less, and hence more PO2 and less CO2. But on average, breathing normally, this is what we're designed to do. Now, what about in the blood, the pulmonary vein? That is the vasculature leaving the alveoli and then going to the heart to be pumped around the body through the arteries. What's its PO2? Well, surprise, surprise, the same as the alveolus, because what's the basic principle of diffusion? Gases move or things move until equilibrium, equal. So it's no surprise that the PO2 and PCO2 of the systemic arterial blood is the same as the alveolus. This is what we're designed to achieve. But what about blood returning to the heart and the lungs, because it's been to the tissues who've taken up some oxygen and CO2? Well, obviously the PO2 is going to be much less. It drops from 100 to 40 on average. Again, if you're running a marathon, it's going to be very different than this. But if you're just quietly resting, it drops to 40, and the PCO2 increases to 45. And that's the story. Before we leave that, you might say to me, looking at those overheads, well, does that mean our bodies use much more oxygen because it drops from 100 to 40 than we produce CO2 because it only goes up from 40 to 45? Well, looking at those numbers, you'd be right to think that, but you would be wrong in fact. Some of you might know, and particularly those who might be doing dietetics or nutrition, who may have looked at metabolism, maybe you haven't at this stage, you might have learnt that normal body metabolism exchanges one oxygen for approximately one CO2. It's not quite, it depends on what you eat, but it's in the range of 1 to 1 or 1 to 0.8. It's close enough to 1 to 1. Now those figures kind of suggest that it's totally different from that. And this is where the solubility comes in. Partial pressures within a liquid is really complex to understand. And the only way I can try and propose it in the way I think of it is that, and again, I don't really care if you understand the explanation as long as you understand the punchline, that dropping from 100 to 40 does not mean that you use more oxygen than an increase of 40 to 45 in CO2. They are approximately equivalent. That's the punchline. Opt out if you don't want to understand the reason, but the reason is partial pressures of gases in a liquid is more about how much you have to add to dissolve it. Now, I thought about this the other day, and or the other year, in fact, and thought, what's the best way to explain this to myself? And it may not work for you, it works for me. You get 2 glasses of water, and you want to dissolve the same amount of a solute in each. But you've got 2 different solutes, one which is soluble. So, Milo. I should have thought of the solutes a bit better, shouldn't I? But anyway, you've got how much Milo do you have to add to that glass to dissolve the same amount compared to how much sugar you have to add to that glass? So, better explanation. 2 glasses, Milo and sugar. Now, the amount of Milo that I have to add to dissolve a set amount is not a lot because it's very soluble. The amount of sugar I have to add, on the other hand, to that glass of water to get the same amount as the Milo is much greater because it's not as soluble. Okay, the sugar is kind of oxygen, the Milo is kind of CO2. So you don't have to add as much CO2, Milo, to your drink to get it dissolved, so its partial pressure isn't as big. Okay, I'm happy with that in my little life of respiratory physiology. Hopefully you will too. If you aren't, doesn't matter. Punchline was all that's important. Explains the difference. Now let's see how it goes around the body. And Silverthorne, lo and behold, I was actually incredibly excited, which shows you how boring my life must be, that in fact I could use a Silverthorne diagram. Lo and behold, this is as good as any diagram that you'd find in other books. So this is Silverthorne, figure 18.2. And it just gives the numbers of what's happening around the body. There's no new information here, but I'm just going to take you through it in one quick discussion. In the air. Now, again, if the numbers are slightly different in the textbook you're preferring to use, don't worry, don't post on the forum, oh, you said 160 and it's 159 in my book. They are approximate numbers for an approximately functioning, quietly breathing individual. Okay. PO2 in the atmosphere, 160. PCO2, much, much less, 0.2, 0.3. Gets into the alveoli, PO2 drops dramatically for the reasons we explained. CO2 increases dramatically for the reason we explained. That diffuses into the pulmonary capillaries. It moves via the pulmonary vein to the heart, gets pumped around the body via the systemic arteries when it goes to the cells. Oxygen moves from the blood to the cells because the cells have a PO2 of only about 40. So oxygen will move out of the blood into the cells until equilibrium is reached. The cells have a PCO2 of 46, so CO2 will move out of the cells into the blood until equilibrium is reached. And therefore blood leaving the tissues via the veins to go back to the heart, to be pumped to the pulmonary arteries, back to the lungs, will have a PO2 of about 40 and a PCO2 of 46. And that's kind of what's happening, PO2 and PCO2 in the body. Now, this is gilding the lily somewhat. I'm just looking at them in isolation, just so you get this important concept. Won't spend a lot of time. Blood returning to the alveoli, PO2 of 40, PCO2 of about 45, 46. It gets to the alveolus, big concentration gradient in oxygen, big concentration gradient in CO2. The numbers aren't the story, as I said. So oxygen will move out of the alveoli into the capillaries, CO2 will move out of the capillaries into the alveoli until equilibrium is reached, and that's what pulmonary respiration is all about. Bigger the gradients, more will move. Tissue respiration, same difference. PO2 of blood coming to the tissues is about 100. Yeah, this textbook's got a little bit less because the heart takes up a bit of oxygen. Look, they're right, but let's not confuse this too much. PO2 about 100, PCO2 40. Again, concentration gradient between the blood and the tissues. Therefore, oxygen moves into the tissues. CO2 moves back into the blood from the tissues until equilibrium is reached, and it returns to the heart as a continuous cycle. And that's tissue respiration. Everyone happy enough with that? Okay, how does that change with ventilation? And this is a really key diagram. Widmeyer figure 1222, Silverthorne 1713 look at the same issue. And this, I think, is the best diagram to explain how changes in your breathing or ventilation affect partial pressures. Let's explain it briefly. And I think this is the second last slide, so we're back on track on our timing. Partial pressures on the y-axis in millimetres of mercury. X-axis is your alveolar ventilation. Remember, I'm not interested in pulmonary ventilation. I'm only interested in alveolar ventilation. That is how much atmospheric gas gets to your alveoli. Now, normally, you and I are designed to breathe to achieve an alveolar ventilation of about 4 litres. That's what we're designed to maintain. That's our homeostatic set point, depending on your size. So at an alveolar ventilation of about 4 litres, our PO2 in orange will be about 100, as we've said. Our PCO2 in green will be about 40. Now, what happens when you hypoventilate? That is, your alveolar ventilation decreases. Well, with decreased alveolar ventilation, look what happens to the PO2. It dramatically and rapidly drops. So halving your alveolar ventilation has quite an impact on your PO2, and if you decrease it any further, it massively decreases your PO2, such that at a rate of about 1 litre per minute, we will have no fresh oxygen. It's unsustainable. You'd die. So you can see by the shape of the orange line that underventilating or hypoventilation is critical to your sustaining PO2 levels in your blood. Now, what happens if you increase your ventilation? Well, it's not as dramatic. We're not designed to respond to increases in ventilation too much. But nevertheless, if you did hyperventilate, PO2 levels would increase, but not dramatically so, as you can see in the upper part of this orange line. Now let's look at CO2. Because as I flagged earlier, CO2 is probably the thing that's going to kill you or cause problems. So, underventilation. What happens to PCO2 in your blood via your alveoli when you underventilate? Again, any reduction in alveolar ventilation will increase your partial pressure of CO2, and it gets to a point that it increases very dramatically. So this becomes a very dangerous area when your CO2 levels are getting so high that it will affect body function for reasons I'll discuss next week. And what about increasing your ventilation? Well, increasing your ventilation, where you're getting proportionally more atmospheric gas, will decrease partial pressures of CO2. Now, whereas there's not a real problem of having too much oxygen in the body, there is a problem with having too much CO2 in the body. Any idea, and I'm asking a question that I don't really expect you to have an answer for, but I'll ask anyway. Any idea why increasing CO2 is a problem to us? When somebody hyperventilates, what might they experience? Does anyone sort of hyperventilated either voluntarily or they use the word hysterical hyperventilation that's not meant to be psychologically implication. Yeah.
I know someone who suffered temporary paralysis.
Exactly. Good point. You get very dizzy and your muscles become permanently contracted, so that static paralysis. So that tells us, and it's not so much the small increase in oxygen that does that, it's the decrease in CO2. The dizziness is easy to explain. Now, in the brain, remember you might have heard in year one, if you did physiology in year one, or elsewhere, if you haven't, but how do blood vessels tend to respond to increases or decreases of carbon dioxide? So if you have a decrease in CO2, a blood vessel is going to dilate in order to get more blood there and flush it away. But similarly, particularly in the brain, decreased CO2 will actually cause the blood vessels in the brain to constrict, to allow the CO2 to build up. Now, the problem with having less blood flow to the brain, you start to feel dizzy and may even lose consciousness. So that's why hyperventilation has as one of its symptoms feeling dizzy and perhaps even losing consciousness. The permanent constriction is related to the muscle, and we'll talk about that another time. Good point. So that's why CO2 is kind of critical, but it tells you small changes in ventilation can lead to big changes in your partial pressures, which is not good for you. And finally, how well are we designed? It comes back to how well we're designed for all this. And like everything else about the lungs, we are fantastically designed to achieve diffusion rapidly. Fick's equation is so good that we get diffusion rapidly. Now, very quickly, the y-axis is pulmonary capillary PO2, that is the PO2